In this video, I want to do a quick review of conditional probability, Bayes' theorem, and likelihood and maximum likelihood methods. Before I go launching into conditional probability and Bayes' theorem, I should probably get a little bit of notation straight so that I'm clear. I'm going to say PA is the probability of A happening. So whatever event A is, PA is the unconditional probability of A. If we have no additional information, it's the raw probability of A. The conditional probability of A would be something like PA given B. This vertical line, it means given. So if we know that event B has already happened, if knowing B changes the probability of A, then this is the conditional probability of A. So this is the probability of A conditional on B. Let's say this is California. The unconditional probability of rain on a given day is probably like 0.1%. But if I know that it's cloudy, B, the probability of it raining, given that it's cloudy, is going to be higher. So the conditional probability of rain given clouds is much higher than the unconditional probability of rain with no additional information. And Bayesian statistics is all about this making use of other information to update our ideas about what the probability of some event should be. So Bayes' theorem of conditional probability, on which all of Bayesian statistics is built, goes like this. The probability of event A given we know B has happened is the unconditional probability of A multiplied by the conditional probability of B given that A has already happened, divided by the unconditional probability of B. This will either immediately make sense to you or seem nonsensical to you. I have not yet figured out what it is that divides people into those two groups. So this is Bayes' theorem. I'm not going to bother proving it. If you need proof, I think I've linked out to a derivation over at Khan Academy. I'm just going to go straight into illustrating how useful this is with an example. I work in a mortality lab, so I think everything should have to do with death. But as it turns out, conditional probability can be really useful for mortality calculations. Let's say I'm looking at American mortality data for the last 15 years, and I pick a random American. Let's call him Arthur Dent, who happened to be alive on the 1st of January in the year 2000. And I want to know the probability that he died before the beginning of 2001. I know from the data that in the year 2000, 2.4 million Americans died out of a total of 275 million Americans who started the year. So the unconditional probability of dying, P dead, probability of being dead at the beginning of 2001, is 2.4 million out of 275 million, which is that many. But what if I have more information about my random American? Maybe I can use that information to update my estimate of the probability of his dying. Let's say I know my randomly selected American was a senior citizen. How do I calculate probability of death given that he was a senior? I mean, I could just look up the death rate for senior citizens, but that's actually what I'm going to use to check my result at the end. we're going to use Bayes' theorem. So the probability of being dead, given that you're a senior citizen, is the unconditional probability of being dead times the probability of being a senior, given that you're dead, divided by the probability of being a senior. So I'm just going to write down a bunch of things that I know and then plug them in over here. So I know the total population in 2000 was 275 million. The number of seniors at the time was 16.6 million. Total number of people who died, oops, was 2.7 million. The total number of people who died was 2.4 million. And the number of dead seniors was 1.36 million. So that tells me the probability of dying so I've already established the probability of dying, the unconditional probability of dying. What's the probability of being a senior given that you died? That's just how many of those dead people were seniors. So P senior given dead is going to be the total number of dead seniors divided by the total number of dead. And the probability of being a senior is just the number of seniors divided by the total population, which is 16.6 over 275. So if I plug these back in over here, we get P dead is 0.00873. Probability of being a senior given that you died was 0.57, and the probability of being a senior was 0.0604, giving an overall conditional probability of dying if you're a senior citizen of 0.824. So 8% of all senior citizens died in that year. And if I go back to my original information and just look at the death rate among seniors, which is dead seniors divided by total seniors, I can check that 1.36 million dead seniors out of all senior citizens is also 0.0824. Shit. Is about 0.0082. No. Is about 0.082. So about 8% of senior citizens die every year, if it's the year 2000 in America. And I can check that by saying, okay, well, according to this raw data up here, the probability of dying given you're a senior is just the death rate among senior citizens. So we had 1.3 million dead senior citizens divided by 16.6 million total senior citizens is also about 0.082. So my point here is that Bayes' theorem totally works. Although obviously it's more useful in situations where you can't just jump straight to the answer and you have to actually go through your conditional probabilities. Another language note, this part of Bayes' theorem which is kind of the inverse probability of the one you're looking for. If I want P dead given senior, P senior given dead is also called the likelihood of being a senior given that you're dead. So for any conditional probability, this sort of inverse thing is the likelihood, or is a likelihood. And this is going to come up pretty soon. One really common application of Bayes' theorem comes up in medicine. I'm just going to mention this. When you're doing testing for diseases, every disease, or blah, blah, blah. When you're doing disease testing, all of our laboratory tests have some sort of success and failure rate. So the probability that you have cancer, for example, probability that you have cancer, given that you had a positive test, right, is not the same as the probability of a positive test. It's very possible to get a positive test and not have cancer. It happened to my dad last year. It was very stressful. So when we know things about the false positive rate of our tests and the actual rate of the disease, or the prevalence of the disease, then we can make better probabilistic estimates of the probability that you actually have cancer if you tested positive, right? So we'd say it's the unconditional probability of having cancer, right? What's the rate of cancer in the wild? Times the probability of a positive test, given that you have cancer, all divided by the probability of a positive test. Well, what's the probability of a positive test? Then we can invoke something called the law of total probability, I should say. So the top on top is not going to change. But the overall probability of a positive test is going to be probability of a positive test given that you have cancer plus the probability of a positive test given that you don't have cancer, the false positive rate. So whenever you're seeing the doctor and they do tests on you, if your tests come back positive, remember the thing you need to actually worry about isn't just that you got a positive test, it's how that affects your probability of actually having the disease they're testing you for, which depends in strong ways on the false positive rate of the test. Another really cool application of Bayes' theorem and what we call Bayesian updating is the spam filter in your email box. So your spam filter uses an algorithm that says, for any incoming message, the probability that it's spam, given the content of the email, is the probability of those words being in an email, given that it's spam, times the probability of it being spam, all divided by the probability of seeing the words in the email. So every time you tag something as spam, it teaches your spam filter how the presence of those words affect the probability of it being spam. Now, every time you tag something new as spam, it takes all the words that are in that spam message and changes the probability of finding those words in a message, given that a message is spam. My last example of Bayes' theorem is my absolute favorite application of conditional probability, the Monty Hall problem. I am old enough to just vaguely remember a show called Let's Make a Deal. It was a game show on TV where someone was chosen from the audience, a contestant is standing in front of 3 doors, door number 1, door number 2, number 3, and they're closed. And the host, Monty Hall, says, behind one of those 3 doors is an amazing prize, usually a car. And so the contestant says, well, I'm going to say it's behind door number 1. They choose whatever door they choose. After they've chosen a door, Monty opens one of the other two doors and reveals that behind that door was a booby prize, usually like a goat or something. And then the contestant is given a choice. They can either stay with the door they originally chose, or change their mind and go with the other remaining closed door. The probability problem here is, which is a better strategy? Should you keep the original door or switch to the other door? So over here I have my little Monty Hall problem diagram. So I'm going to call these doors A, B, and C without losing generality here. And I want to know if I, as a contestant, initially chose door A, and then Monty opened door B, what's the probability that I'll win if I stay with door A? Most people say, well, since it's either behind door A or door C, because we know it's not behind door B, it being the car, then it should be a 50-50 shot. But this is not actually the case. So we want to know the probability, given this particular arrangement of doors, probability that I win with A, given Monty opened B. By without loss of generality, I mean that this is going to be the same as the probability that I win with A if Monty had opened this door and there was a goat. So that's going to be the probability that I win with A times the probability that Monty opens B, given so I want to know the probability that the prize is in A, given that Monty has opened door B. So that's going to be the unconditional probability that the prize is in A times the probability that Monty opens B, given that the prize is in A, all divided by the probability that Monty opens B. So if we just think this through for a second, the unconditional probability that the prize is behind door number 1 here, door number A, we'll assume that the game is fair and random and say that there's a 1 in 3 chance that they put the prize behind door A. Now what's the probability that Monty's going to open door B given that the prize was in A? Well, if you've never seen the show, he never just straight up opens the door that you've chosen and said, "Congratulations, you won," right? No matter what door you choose, he always opens one of the other two and shows you a goat. This is important for the probabilities all adding up. So since you've chosen A and he has to open a door, we'll assume that he's fair and he always 50-50 opens either B or C. And finally, the probability that he opens door B without knowing anything about where the prize is also 1/2, right? Because he never opens the door you've chosen. And that means that the probability that the prize is underneath the door that I've chosen unsurprisingly, it's 1 in 3, right? The fact that he showed me a goat doesn't change the fact that there was always a 1 in 3 chance of me having chosen the correct door the first time. It gets more interesting if you want to know, okay, what's the probability that the prize is in C? So this seems obvious to me, and I've always loved the Monty Hall problem because it seems obvious to me. You should switch. When Monty says, do you want to stick with door A or switch to door C, you should always switch, because there was only a 1 in 3 chance that you're right, which means there's a 2 in 3 chance that it's over underneath door C. If you don't believe me, which a lot of you won't, you can calculate it. Probability that the prize is underneath C, given that Monty opened B, and you originally chose A, is the probability that the prize is in C, unconditionally, times the probability that he opens up B, given that the prize is in C. Divided by the probability that he opens B. So in this scenario, remember, you chose A in the beginning, which means the probability of the prize being under C is still unconditionally 1/3. But now, what's the probability of Monty opening B if we know the prize is in C? Well, if I've chosen A, and we know that the prize is over here, Monty has to open B, and he'll open B 100% of the time if the prize is underneath C. And the unconditional probability of B is still the same, 1/2, which means that if I've chosen A, the probability that the prize is underneath door C is 2/3, so you should always switch. If they revive the show and start doing Let's Make a Deal again, and you get chosen, pick a door at random, but always, always, always switch to the other one when they ask you later. Because this is actually a very famous problem in statistics, in the history of statistics. And if it didn't make sense to you, I recommend both going to YouTube and looking up old episodes of Let's Make a Deal so that you understand what's behind door number 1, door number 2, door number 3 comes from. And also look at some of the articles people have written debating whether or not the probability that the prize is underneath door A and door C is 1/3 and 2/3, like I say here, or 50-50, the way a lot of people's intuition says that it should. Because this is actually a very famous problem in statistics, in the history of statistics. And if it didn't make sense to you, I recommend both going to YouTube and looking up old episodes of Let's Make a Deal so that you understand what's behind door number 1, door number 2, door number 3 comes from. And also look at some of the articles people have written debating whether or not the probability that the prize is underneath door A and door C is 1/3 and 2/3, like I say here, or 50-50, the way a lot of people's intuition says that it should. So if you've ever read a paper that involves Bayesian statistics, or a model that uses Bayesian updating or something, they use a lot of language that doesn't appeal to me intuitively, so I have to remind myself, so I'm going to remind you. Bayesians talk about posteriors and priors and likelihood functions. You can think of it as them referring to different chunks of that expression for conditional probability. Right, so if we're talking about the conditional probability of B given A being the unconditional probability of B times the probability of A given B divided by the probability of A. I think I reversed the A's and the B's to how I've been doing it before, but it's the same. And this bit over here is the posterior. Right, it's the conditional probability of B after we take into account all the stuff we know about A. This bit over here, the unconditional probability of B, is the prior, and this bit over here is the likelihood. So the prior kind of makes sense because it's what you thought the probability of B was before you had any information, right? Prior to getting any information about A having happened. And sometimes you'll see this bit down here referred to as evidence. And the thing I want to spend a little bit of time talking about is the relationship between likelihood and probability. Because it's a fiddly distinction, but an important one to get straight, especially when we talk about likelihood methods and maximum likelihood methods. So right, likelihood and probability are closely related concepts that a lot of people find difficult to keep straight, myself included. So in a statistical context, you can think of likelihood as being the mirror image, or sometimes people say the inverse, of probability. Well, let's consider that for any probability function, the probability that your random variable is equal to some value, given your assumed probability distribution, what that really means is what's the probability that my random variable takes some value, given I'm assuming a probability distribution with parameters n and p, or whatever the parameters of your distribution are. If it's a binomial distribution, say, I've chosen n and p. Right, so what's the probability of my data given the model I'm using, the assumptions I've made, or the model parameters, really? So we can approach this the other way and do the inverse of this, the likelihood, then, the likelihood function, the likelihood of my model parameters given the data is the same as what's the probability of my model parameters given x is equal to small x. Right, these things are just reverses of each other. So for any given model, essentially the probability function and the likelihood function are the same equation, but the probability is a function of the data with your parameter values fixed, your model parameters fixed, and the likelihood is a function of the parameter values and the data is fixed. And this equality sign isn't really fair, because while every likelihood value is a notional probability, the likelihood function is not a probability density function. It doesn't have to enclose an area of 1. So what do we use likelihood for? Well, if I have a bunch of data and I want to fit a model to those data, I want to fit a model that produces the biggest likelihood of producing the data that I found. That's why we call it maximum likelihood. You take the likelihood function that drops out of the model you've chosen, and then choose model parameters that give you the maximum likelihood of getting back your data. Right. So the best model parameters are the ones that give you the maximum of your likelihood function. So how do you find the maximum likelihood? The same way you find the maximum of anything. You have a likelihood function, which is usually the probability distribution function of whatever model it is you've chosen, whatever probability model it is you've chosen. And then you use simple optimization to find the maximum value of that likelihood function, or to find the parameters that maximize your likelihood function. I have some experimental data and I want to fit it into a binomial distribution. So I have to find the binomial parameters that maximize the likelihood of my model returning the data that I found. So the likelihood function for the binomial, which is the likelihood of p, the binomial coefficient, given some experimental data, the number of experiments and the number of successes, is just the same as the probability density function, and choose y, p to the y times 1 minus p to the n minus y. So given I've done n experiments and had y successes, this is my likelihood function for a binomial probability p. So for example, say you're studying predatory shorebirds, and you've watched a bunch of them hunting. You saw them do 11 dives, and on 7 of them, they successfully caught fish. So we're trying to fit a model for the binomial probability of a successful dive based on this data. I want to know what value of p should I use for the per dive success rate. And I'm assuming the success rate is going to be binomially distributed. So if I take my likelihood function here, I want to find its maximum, given n and y are 11 and 7. To find the maximum, you'd like to find where the derivative of my likelihood function is 0. This doesn't look like a lot of fun to take the derivative of, so I'm going to use a trick. If you have a likelihood function, you will get the same maximum likelihood if you use the log of the likelihood function. So my log likelihood function, p given 11 and 7, is going to be log 11 choose 7 plus 7 log p minus 4 log 1 minus p, which is much easier to take the derivative of, right? d by dp of my log likelihood function. This just goes away, so I get 7 over p minus 4 over 1 minus p, and I set it to 0 to find where the maximum is, which returns p is 7 over 11, which is probably what your intuition told you right away. If I observed 7 out of 11 successes, the best description of that data is going to come from a model that assumes the probability of success is 7 over 11. So the maximum likelihood estimator of the probability of success of diving for these fish under a binomial distribution is 7 over 11. Right? So in practice, after you've decided what distribution you're trying to fit, you can plug your data into the likelihood function for that model and find the parameters that will maximize the likelihood of getting back your data. And if your likelihood function is ugly, which they usually are, you can just take the log of both sides and often get a problem that's easier to solve, which is why everybody talks about log likelihood functions all the time. And I think that's about all I want to say about probability and likelihood for now.